let's move on to the last speaker of this section, Pablo Lopez Rios, who tell us about optimizing Jastrow factors.
Okay, can everyone see my screen?
Yes, we can.
Okay, great. So so I work in the Alavi group in Stuttgart, and so we are also in T-Rex, and this talk has a lot to do with the previous one, because we're basically doing TC Hamiltonians as well. We call them similarity transformed. And the difference is that we are combining these similarity transformed Hamiltonians with the FCI QMC method, which is a projection type method that basically takes your, takes an initial wave function represented as Walker's on determinants and applies imaginary time evolution to project out the closest state to the ground state as you can possibly represent with a certain number of Walkers. So this is the master equation of the FCI QMC method. And then what happens typically in FCI QMC is that you're missing, so when you have a few determinants, you're describing your static correlation quite well, but you are missing dynamic correlation. And so from different type of methods, VMC and DMC, which are real space methods, we know that Jastrow factors are this thing that allow you to describe dynamic correlation in a very compact manner. And by contrast with FCI QMC, VMC and DMC struggle to describe static correlation, but dynamic correlation is something that they can do like very easily. So the idea here is to combine, as in the previous talk, is to combine the use of a Jastrow factor with these quantum chemical methods that are very good at describing certain types of correlations, and particularly are very good at describing energy differences, whereas VMC and DMC are typically very good at describing total energies, but not particularly good at error cancellation. Which are two things that need to be balanced out, of course. So, so the way we do the transcorrelation here, the similarity transformation here, is, well, it's based on the same principle. Basically, you can write a modified Hamiltonian where you apply the similarity transformation and you get a new Hamiltonian that then you can use in a projective method without having to worry about left and right eigenvectors. You just solve for the right eigenvector, and the left eigenvector you don't need to construct or ever even have to consider, basically. So that's where your Jastrow factor goes. And then you you change your usual evolution, your imaginary time evolution, which in FCI QMC basically takes you from the Hartree-Fock energy all the way down to whatever fully correlated energy you find for a certain number of random Walkers. And then when you add the similarity transformation, you start at a lower energy, so at a different reference energy, which is given by this expression here, and that takes you down to a usually an energy that's lower than that provided by FCI QMC, because you add more correlation, more dynamic correlation. So. So basically, this is fairly straightforward, and what I want to focus on is how to optimize the Jastrow factors, which usually come from VMC optimizations in our case, and how to optimize them so that they work in the setting of similarity transformed FCI QMC. So basically, these are just the regular definitions of the one and two body operators, and then when you apply the similarity transformation, you get a three body term as well. and a modification to the two-body term that makes the problem non-hermitian. Again, this doesn't affect FCA QMC in the slightest really. Oops. So one of the things we have looked at is at reducing the memory usage, etc., using things like neglecting terms and using on-the-fly evaluation with resolution of the identity property combined into it, so that we can do things more efficiently, etc. But in the end, we've realized that basically we can store these 6 index integrals for a basis of 170 orbitals, more or less, with 2 terabytes of memory, which is the largest memory we have accessible in our group, in the computational resources we have. So basically, we don't need to do any of those things to get results for a large variety of small molecules. And then, so another thing, so that we are developing a code called TCH-int. That is a library that can be called by other quantum chemistry codes, so that you can get your 3-body integrals and use them, whether they be pre-calculated and stored in disk or calculated on the fly, etc. And that can be done simply by calling the library. So we make use of the embarrassing parallelizability of the evaluation of these 3-body integrals. Basically, all of them are independent. You have billions of them. So basically, you can divide the evaluation of your integral of your matrix into as many bits as you like, and we can do that. We use MPI with MPI shared memory. We use HDF5 files. We use T-Rex-IO as well, and more support for T-Rex-IO is planned, so that we can store all of the byproducts of our calculation in a way that any other codes can use them. So at the moment, so basically, this is all you need to do to get your 3-body integrals, right? Then TCH-int is made of bits from the Casino continuum quantum Monte Carlo code that evaluates the Jastrow factor, and then the orbitals are evaluated themselves using PySCF, which is called via a Python interface. And then TCH-int currently can be called from NISI and from MolPro via an FCA dump. And there are people in our group doing a couple cluster with a mean field type of approach, where 3-body integrals are folded into the 2-body integrals, right? And they're getting very good results, but I'm not going to talk about that now. I'm going to talk about the optimization. So how is optimization performed in VMC? Basically, VMC samples a trial wave function and generates a set of electronic configurations in real space distributed according to the square of this trial wave function. And then when you have those configurations, then you can choose to minimize the energy or the variance of the energy, or this other alternative, the variance of the reference energy being the first value that I showed here. So the variance of that energy, so this energy is significant because that's sort of the starting point for the FCA QMC calculation. It's more significant to the FCA QMC calculation than the VMC energy itself is. So, okay, so we have 3 alternatives there. And so first of all, let's look at the optimization method. And I'm just going to show one set of results for the C2 molecule, where we try to go from double zeta to triple zeta. And depending on what optimization method we have used, there is absolutely no convergence towards the known binding energy, or there is. So if you optimize the Jastrow by minimizing the variational energy, then you don't get any improvement from going from double to triple zeta. However, if you go from a VDZ basis to a covalence double zeta basis, then you gain something. This just indicates that the Jastrow factor that you're obtaining by minimizing the energy is failing at describing the core region correctly, and you need core functions to fix that. Whereas when we optimize the variance or the variance of the reference energy, both give similar results. Then you go from a certain value to a much better value by going from double to triple zeta, but the core functions do basically nothing. So that's the sort of thing we want to see. So we stick with variance minimization. We've tested other systems as well, and that this is consistent with what we are seeing. The thing is that in VMC, you don't do things this way. You usually want to minimize the variational energy, and that's it, and you're happy with that. But in this case, we really need to tune what types of things we do with the optimizer. And now I want to describe a slightly different problem, which is that when we optimize the variance of the energy, basically we vary the wave function parameter alpha, trying to find alpha 0, and we are supposed to, well, find that minimum, and that should be it. But actually we are using a random sample of real space configuration. So basically you have like error bars on your curve, and when we have a fixed sample of configurations, that's called a correlated sampling approach. Instead of having, we have any curve in the green region here, right? So we have this parabola here, and we're going to find a slightly different minimum, right? If you run another instance of the same calculation, you're going to find a slightly different alpha, etc. And in the end, what you have is a distribution of possible values of the parameters around the true minimum. That means that any function, so the top panel now comes into play, and this is any function of the parameters that is not at a minimum at the same position as the variance is going to be linear to first order. So it's just a straight line. So this variance of the standard deviation of the parameters that you're going to get translates directly into standard deviation of the function that you're going to calculate. That means that when you minimize your parameters in optimize your Jastrow factor, you're going to get a slightly different answer for your FCI-QMC energy, and this turns out to be a significant effect. So we want to reduce to really control how wide this distribution is, so that we get our results to the desired accuracy. How do we go about estimating that? So there are two things that we sort of know from experience. One is that the standard deviation of the VMC energy or the VMC reference energy, so meaning if you run different optimizations, the spread of the energy you're going to get is usually smaller than the standard error of any of those individual calculations of the reference energy in any of those individual calculations. So that's an inequality that we're going to keep there. And then we know another thing, and that is that if the reference energy changes a bit in your FCI-QMC calculation, usually the FCI-QMC algorithm can compensate for that by, well, basically tweaking your multi-determinant expansion coefficients, so that in the end you get roughly the same FCI-QMC energy. So what you can deduct from there is that the standard deviation of the SD FCI-QMC energy is less than the standard deviation of the reference energy. So if we combine these two inequalities and call the like proportionality parameter 1 over r, then we have this expression here. So basically, we choose the number of VMC samples, the number of samples of real space configurations that we use for optimization based on this expression here. So m changes the standard error in your reference energy as it goes as 1 over m to the 1/2, right? And then, so if you have a given target accuracy, then you can find what the value of m is just by inverting this equation with an assumed value of r. And looking at various systems, so this is the typical scatter plot of reference energies versus ST-FCA-QMC energies, which is basically the things I am connecting here are these two quantities. And you can see that basically the scale on the x-axis is about 5 times bigger than the scale on the y-axis. So having done this for a few systems, we sort of assume universally that r is going to be of the order of 5. So that allows us to optimize our wave function parameters accurately, so that we don't get these fluctuations due to the random nature of the optimization process. So now with this, we get to some interesting results. So the C2 molecule, so it takes normal FCA-QMC. Well, you have to go to quintuple zeta to get within chemical accuracy of the known result for the binding energy of C2. Whereas we can get there and stay there by triple and quadruple zeta. So this is not a fluke. That is why we are running this much heavier calculation at quadruple zeta. We are not like overshooting and then maybe coming back. We are hitting the chemical accuracy at triple zeta, and then we are staying there. So that is basically, in this case at least, this is 2 cardinal numbers that we're saving. So 2 basis set orders to zetas, right? So then another tiny problem, and this is a system we've been working with Giovanni Limani. So he was interested in looking at this assembly of 2 hydrogens and 2 helium atoms in a square, because then you get a very hard to describe. I mean, it's very sensitive to your methodology, this singlet triplet gap. So we try to match the CAS-PT2 results. So you can see that the CAS 6 results are basically consistent and well converged with basis set size. If you add a PT2 correction, you go to a slightly different value. You have to assume that this is probably better. And then if we go and do our thing with a Jastrow factor and everything, we get this lone value up here at the double zeta level. And that is not very good. What's happening here is that we really need to take into account that the singlet state is, the kind of ground state wave function, I mean, excited state, no, actually, ground state wave function has 2 very heavy determinants. I mean, the 2 leading determinants come with a very large weight, right? So you cannot neglect the second determinant. And what's happening when we don't have it is that the Jastrow factor is trying to compensate for the correlation that determinant is supposed to be describing. And that is a mistake. That's something you don't want to do. So if your system is highly multi-configurational, you want to have the main multi-configurational character in the wave function you're optimizing, so that the Jastrow factor knows about these determinants and doesn't try to reproduce what they should be doing. when we add that second determinant, then our results are dramatically better and in full agreement with the CASPT2 results. Now, a third case is the CH2 molecule, which is, again, we're doing this with Giovanni Limani, and he ran these calculations with Cas6 and a PT2 correction. And so this is for the triplet singlet gap in CH2, which is not trivial to reproduce. And indeed, the PT2 correction goes in the wrong direction. So it depends on what orbitals are in your active space, apparently, and it's very sensitive. So the PT2 correction is very sensitive to that in this case. But if we just do our Jastrow factor optimization and we do the double zeta and a triple zeta calculation, basically we are within chemical accuracy of the experimental result by triple zeta, which is a very, very encouraging result. I mean, we're running more of these calculations and trying to get a fuller picture. But for now, I think it's safe to say that it's a very promising methodology. And well, I hope I have kind of conveyed the complexity of optimizing a Jastrow factor for quantum chemistry calculations, and there's certainly a lot more work to do. But this is all I wanted to say. So thank you very much.
Thanks. Questions from the audience?
Yes, yes, hello, Pablo. Could you go back 2 slides, please? Yes, so where you talk about the singlet character where you need the multi-configurationality, do you talk about including the second determinant in the DMC optimization?
Yes, yes. So this.
Oh, okay.
Yeah, so sorry, I didn't mention. So this psi is a trial wave function in DMC, which somewhere here I was talking about using just a single determinant, right? And the Jastrow factor is in the presence of that single determinant. This other wave function has an extra determinant with a non-unity coefficient. Yeah. So, yeah.
Yeah, I mean, kind of a follow-up to that, are there kind of plans to going back and forth in the sense of in FCQMC, you then find the n most important configurations and then go back to DMC to get a better Jastrow factor?
Oh yes, yeah. That's something we are going to study. I mean, I'll try that on occasion, and it's usually slightly disappointing. But I think we hadn't kind of nailed the optimization procedure to the level we have now. So I'm hoping to get back to that. It's a very, very interesting thing to do, like close the loop, right?
But that's the last one.
Yes. Yeah, just one short last question, where you discuss the better performance of optimizing the variance of the energy and not the minimum of the energy. Do you kind of, would it be possible to do an optimization with both parameters, for example, or?
Yeah, that is possible. Yeah, and in a way, we sort of do that in the energy minimizer, because we don't minimize the energy, we minimize the energy plus 3 sigma, right? So if you're increasing your variance as you minimize your energy, then that sigma increases so as to kind of preclude going to a very large variance situation. That the parameter in front of that factor of 3 is arbitrary, of course, but it could be tuned so that the variance weighs more than the energy in a way.
Just a comment. This is very interesting. So I was brought up with a variational principle. So yes, I minimize the energy. That's the recipe. But then the last few years, I've been working with Gaussian process regression And then I'm been taught I should minimize the variance to get the most likely function that is represented by my parameterization. And so it's interesting to see here that you're sort of drifting away from the energy variance and going towards the variance, going from the energy minimization to the variance minimization.
Yeah. So variance minimization was the kind of the original method used in VMC to optimize Jastrow factors in the 90s, and only in the late noughties it was that the energy minimizer, the energy minimization technique was kind of refined into a working methodology. So and that's sort of the standard now in VMC, but variance minimization is still an important method, and it's never clear which. In VMC and DMC, certainly optimizing the energy is the right thing to do. It's never clear whether the wave function is actually a better representation of the ground state wave function, or it's just one that gives you a lower variational, after all, energy. So yeah.
Okay, thanks. And let's thank all the speakers of this session.